Hello dear learners, welcome to Pen and Paper Chemistry on YouTube. I hope you all have got this chart ready which makes our learning of the imperfections or defects in solids easy. So let's start with the first defect which we talk about today, and that is the stoichiometric defect. Don't forget the pen and the paper to take down notes for offline reference. So first of all, what is a point defect? We know that in a crystal, the atoms, molecules or the ions, they occupy fixed positions or definite positions. There's a fixed arrangement of these particles when we are talking about a crystal. Now, when there is some foreign particle which enters into these fixed positions, or some of the particle may go missing from these positions, we have what we call as a point defect. The other defects are the line and the plane defects, wherein what will happen is the entire row of atoms or ions has impurity or has some imperfections, or the entire plane is made up of impurities in order to change its properties. Point defects are further classified as stoichiometric, non-stoichiometric and impurity defects. Stoichiometric defects are also called as intrinsic or thermodynamic defects. Now, before we go on to the details of this, first let us understand what is stoichiometry. We all do it in grade 11. You write the formula of compounds, for example, NaCl, CaCl2, potassium nitrate. Now we know that these crystals are, so when I'm talking about potassium nitrate, it is made up of 1 potassium, 1 nitrogen and 3 oxygen atoms, or 1 potassium ion and 1 nitrate ion. So the ratio, the molar ratio of potassium to nitrate in a crystal of potassium nitrate is 1:1, and that's the stoichiometry. As simple as that. So when I'm calling it as a stoichiometric defect, that means the stoichiometry does not change. When you see from outside, the crystal looks very, very normal. You can't make out from outside. So the formula still remains the same. So your sodium chloride would still be written as NaCl. Calcium chloride will still be written as CaCl2. So that's what we've written. The formula does not change. The number of positive or negative ions are the same, or for that matter, the formula of the molecule of a compound will also remain the same. I introduced the terms intrinsic or thermodynamic defect. Intrinsic properties. Do you remember the term intrinsic or intensive properties in thermodynamics? Yes, the inherent properties which do not depend on the quantity of substance taken. So these impurities are there in the crystal irrespective of whether I'm talking about 1 gram or 1 kilogram of the compound, as long as they are prepared by the same method. Thermodynamic impurity. Now, as I mentioned earlier, we have done in the previous video the third law of thermodynamics, which says that at absolute zero, the entropy of a perfectly crystalline solid is 0. That means there is no randomness, there is no disorderliness. Now, we know that a point defect arises at high temperature, meaning the entropy will increase and it will no longer remain a perfect crystal. Just like when we are angry, we are no longer our perfect self, right? So, a thermodynamic defect. Stoichiometric defects are further classified into Schottky and Frenkel defect. Now, in order to remember and understand these defects, study the structures. Now, the first one that you can see on your screen is a Schottky defect. Observe. I've marked over here the cations that we've taken are the silver and the anions are bromide. So, what compound are we talking about over here? Yes, we are talking about a crystal of AgBr, silver bromide, right? Now observe carefully the diagram that we've drawn. You've got silver, you've got bromide, silver, bromide, silver, bromide, silver, bromide, and now there's an empty space here. So what is missing? Silver. Let's go on. So we've got silver, another empty space. But what is missing this time? Yes, it's the bromide which is missing. One silver, one bromide. If I go through this crystal of silver bromide in 3 dimensions, presently we are just taking it as a small part of it. We are taking it in 2D to understand things in an easier way. So when you go in 3D, you will find that the ratio of the silver ions missing to the bromide ions missing is the same. It will be 1:1. For every silver ion missing from the crystal, there will be 1 bromide ion missing. In other words, what have they created? When they have gone missing, they have left a vacancy here, right? In other words, this is a vacancy defect. Now, because silver and bromide have gone missing, so there will be more than that also, right? So, we've taken only example of one silver and 1 bromide. When we are talking about a crystal, there could be more silver and bromide ions missing. What will happen to the mass of this crystal? Of course, the mass will decrease. Now, density is defined as the mass per unit volume of a substance. If mass decreases, what will happen to density? Yes, of course, in this case, the density of the crystal will decrease. But the interesting bit is that these holes, these vacant sites can actually start moving. They can exchange places with the other ions. Same way, the second one can also move in order to exchange places with the other ion, right? So that means these vacancies can move, these holes can move, making the crystal a conductor. Now, since positive and negative ions have gone missing, tell me, will this crystal become positively charged or negatively charged? Yes, of course, since both are missing in equal numbers, this crystal as a whole still remains neutral. So let us jot down our points for the Schottky defect. First one, we say that equal number of positive and negative ions are missing from the lattice site. That is why it's an example of a vacancy defect. Electrical neutrality is maintained. Yes. The unoccupied lattice points are what we call as holes. As I explained earlier, since the mass decreases, the density also decreases. What kind of compounds show this defect? This is usually shown by compounds wherein the coordination number is high. That means they are surrounded by a large number of oppositely charged ions. But for this defect to be successful, the size of the cations and the anions should be similar, more or less equal, because they are going to compensate for each other's absence. We usually find these kind of defects in the alkali metal halides. So sodium chloride, potassium bromide, cesium chloride, and of course AgBr. We gave that example, right? Let us now introduce another defect, what we call as Frenkel defect. It's a very, very important one. Again, I'm taking the example of silver bromide. So, does that mean silver bromide has both the defects? How is it possible? How can it have both the defects? We'll discuss about that later. You may think about it after I have explained to you what is Frenkel defect. Observe the crystal again. Silver bromide. Yes. Silver is missing. But where is that missing silver? I don't see another hole in this. Oh, the silver is still there, but it's gone hidden. It's occupying a space in between. So just like, imagine these are the students of your class sitting on their respective chairs and desks. But one naughty student decides to move out from his chair or desk and goes and starts chatting, standing next to another student and starts chatting over there, right? So interstitial, it's not occupying the place which is designated for it, what we call as the lattice point. It's occupying an intermediate or interstitial position. So, what kind of defect is this? I have a vacancy over here, but at the same time, this hasn't gone missing completely. It's occupying an interstitial position. So, it's a vacancy defect, yes. But at the same time, that ion is occupying an interstitial position as well. So interestingly, in the same example, you are observing two defects, vacancy and interstitial defect, right? Interesting, right? So that means we do have a hole. What about the charge? So does that mean my ion will become positively charged? No. Since the number of positive and negative ions are still remaining the same, because this hasn't moved out of the crystal, remember? So that is why again our molecule will be electrically neutral. What about mass? Will the mass change? No, mass will also not change. It will remain the same because again the ion hasn't gone out of the class. It's still in the class. So what about the density? Yes, of course, the density also remains the same. So let us jot down our points for Frenkel defect. Frenkel defect is where an ion goes missing from its lattice site and occupies an interstitial position. That is why we've called it as a vacancy and interstitial defect. Are you all writing it down? You won't have time to come onto YouTube when you have exams, right? So write it down. If you write, your confidence will also grow in the topic. So go ahead, don't be lazy. Come on, pick up a pen and paper. Electrical neutrality, yes, very much maintained like the Schottky defect. We will have holes here, yes, hole is created here as well. That's what Frankl says. Mass decreases, mass does not change. So here we have a difference here. So the density decreases, density remains the same in the case of Frenkel defect. Here we said that Schottky defect is shown by compounds which have high coordination number. Here it will be shown by compounds which have low coordination number. In other words, there's less crowding in the class. This ion can only go and occupy an interstitial position if there are less students in the class. If my class is crowded, look at that. Do you think that my ion can go and fit itself somewhere? No. So preferably this takes place in the case of compounds which have low coordination number and large difference in size of cation and anion. Usually it's the cation which is smaller. Remember, we did it in the periodic table. The cation is losing electrons, right? Because it is losing electrons, the size of my cation is smaller than the size of the anion if we are comparing atoms falling in the same atomic radii range. Look at the examples in the case of Frankl defect. We have almost all the silver halides except AgF. So AgCl, AgBr, AgI, zinc sulfide. Yes, they are able to conduct electricity. They act as solid electrolytes, such kind of solids. Now the question here is, I gave you the example of silver bromide under Schottky as well as Frenkel defect. So does that mean that my silver bromide categorizes under both these defects? Have you written them down? Have you written down the points? Go ahead. So the question remains, yes, if we see the radius ratio for silver bromide, it's intermediate between the low and the high values. It is falling in the range of 0.414 to 0.732, where the coordination number is 6. So it is neither a high nor a low value. We said we need a high radius ratio and a low radius ratio. So high coordination number, low coordination number, but it's got an intermediate value. So that is why our silver bromide is able to show both Schottky and Frenkel defect, because it's got a cubic close packing arrangement of bromide ions, whereas silver is occupying the octahedral holes. Now when it is occupying the octahedral holes, it can always take that opportunity to jump into a tetrahedral hole to fit itself there. Interestingly, Shorty defect is found much more commonly as compared to Frenkel defect. In the case of Shorty defect, we notice that the coordination number is high. But at the same time, in the case of Shorty defect, what will happen is the ions simply go missing, right? They're not standing in between, they're not standing midway, and they are not, being close to ions of similar charge. So there's no problem for them. Here, they've simply gone missing. Whereas in the case of Frenkel defect, what is there is that you need a high energy in order to move the ion from its position in order to make it occupy an interstitial position. To put it more technically, we say that the energy needed to develop Shorty defect is lower than that required to develop the Frenkel defect, because you need a high enthalpy in order to fit ions into interstitial positions. Why are these defects developed? How do they affect the behavior of the crystal? Simple. When you are talking about, say for example, Frenkel defect, what is happening? The ions with the similar charges here, they are coming close to each other, right? The proximity increases. Here also there are holes in the case of Shorty defect. So this affects the dielectric constant as the similar charges come close to each other. Not much detail is required about this. It's just to make sure that we understand the whys and hows of things. We did earlier, the holes can shift and so conduction of electricity can take place. The presence of holes, what will it do? It will decrease the stability of the crystal because again, the ions of similar charges are going to come close to each other, and do they like it? No, they don't. Here also there are gaps created. The gap is bringing the earlier, if I put the silver ion over here, so it is the forces of attraction between oppositely charged ions which are holding them close to each other. Now, no silver here means there is nobody to hold these bromide ions in place. So, we notice that the lattice energy or the energy required to break this crystal would be less. The stability of the crystal will decrease. More appropriately, lattice dissociation energy. I hope you are enjoying these lessons. Do let me know how you feel, or if there is any other topic you would like me to cover on the channel. Next video, we shall be talking about the non-stoichiometric defects. So take a break, revise, write, and get ready for the next video. Take care, stay safe.